This video is our first introduction to graphing exponential functions versus logarithmic functions, and it'll take us a couple days of practice, but we're going to do some experimenting with some graphs first, and then gradually our homework problems will get a little bit more difficult. So first we need a reminder that we have already learned what logarithms are. Logarithms are exponents, so we could compare these two expressions. If we have 2 to the third equals 8, we all believe that's true. 2 to the third power produces 8. So we could rewrite that in this form. So remember, the symbol for logarithm is log, and then we say what our base value is. So our base from this expression is 2. And the result that we want to produce takes this position. And what we're looking for then, when we're looking for the logarithm of 8 in base 2, you have to say to yourself, I'm looking for what exponent I put on the base in order to turn it into a result of 8. And the logarithm itself is the exponent. The log is the exponent. So you will hear teachers say that all the time. Don't make logarithms difficult. Logarithms are simply exponents. So we read this as the logarithm of 8 in base 2 is equal to 3. So a few examples here. Exponents, even if I asked you for the base here, I think you could come up with the base must be 2 if we can raise it to the 4th power and get 16. Now, algebraically, I hope you'd also say, why can't it be negative 2? And that's true in the exponential form. But when we do logarithms, we're going to stick with the positive values. So this statement in A should give us a big clue about the statement in B. Our base is 2, so we're looking for an exponent on the base 2 to produce the result of 16. So we just found out that 2 to the 4th power, so our x value is the exponent that we're looking for, and we know that we're looking for an exponent of 4. 2 to the 4th power is 16, so the logarithm of 16 in base 2 is equal to 4. Okay. In C, we want to put an exponent on 3 to turn it into 1 over 81. Well, 3 to the 4th power is 81. So to do a reciprocal, we use a negative exponent. So 3 to the negative 4th power is 1 over 81. So now we write it in log symbols. We want a result of 1 over 81. And our base is 3. So the logarithm is the exponent. We're looking for an exponent on the base 3 that turns it into a result of 1 over 81. So x is equal to negative 4. So we just have to get back into the swing of using logarithm symbols for exponents. Okay, now we're going to put these into function form. So we're going to stick with a base 2 here to keep it simple as our first example. So we're going to put f of x is equal to 2 to the x into GeoGebra. And g of x is the log of x in base 2. And we want to see how these two things compare to each other. Okay, so let's go to GeoGebra, and we'll start with a blank window here so you see how we can enter these. So first, if I want to enter a function f of x, and I want to make this 2 raised to the x power, and I didn't put an equal sign is why it didn't recognize that. All right, so there's 2 to the x power, and I think we know quite a bit about this already. I think that you know if we put a 0 in for x, we get a very obvious point, because 2 to the 0 power produces 1 as our y-coordinate. And think if we put 1 in for x, of course, when x is 1, we should get a y-coordinate of 2. When x is 2, we get a y-coordinate of 4, and the function rises very quickly. We know, for example, that 2 to the 5th power, when x is 5, our y-coordinate is 32, and of course it's way off the top of the graph. let's make sure everybody understands why the graph is getting so shallow on the left side. What happens when we let x be -1? Look at our function. 2 to the -1 power is 1/2. What if we have -2 for the x coordinate? 2 to the -2, we square it and we flip it over. So we would be at 1/4. And if we put -3, 2 to the -3 would be 1/9, and then 1/16, and then 1/32. So it's going to be getting smaller and smaller, but never 0. So we say that, and in fact, if I slide the graph this way, you can see that it never actually hits 0. It's hard to see that on GeoGebra, but 2 to the -10th is going to be 1 over 1024. So it's almost 0, but always above 0. So we say this line is an asymptote. A-S-Y-M-P-T-O-T-E. Asymptote. All right. So let's now go back then. Let's get some space here. And let's compare a logarithmic function. So I'm going to let g of x be equal to, and now GeoGebra can't do a subscript in the input line, so our notation is to type log and then parentheses, and then we put our base first. That's going to be 2, comma, and then here my variable x. And you'll see as soon as I hit enter that it moved that 2 to our base. So here's our graph of the log of x in base 2. So now we have to reverse our thinking. Now x is the result. So when we have a result of 2, we're looking for what exponent do we put on the base to turn it into a result of 2. Let me say that again. The base is 2, and if x is 2, we're saying what exponent should we put on 2 to turn it into a result of 2? And that should be a value of 1. So do you see that right here where I'm pointing? There's going to be a value of 2, 1. Let's look at this intercept point. Why should this intercept point be here at 1, 0? Let's put 1 in for x and think about it. 2 to what power would give us a result of 1? Well, no matter what the base is, the exponent to get a result of 1 will always be 0. 2 to the 0 power produces 1. So for logarithms, we've got to think backwards. What is the logarithm of 1 in base 2? That would be 0. How about down here? How can I come up with x coordinates like, how can I come up with values here? What exponent would I put on 2 if I wanted to come up with 1/2? Wouldn't that be -1? So if x is 1/2, I'm looking for the exponent to produce 1/2. How about if we have 1/4, then our exponent would be -2. Do you sort of see that we're reversing the x's and y's between these two graphs? And that's the point of the lesson. So now we want to look a little more closely, and I've already made a GeoGebra file where I've used some color coding. So I'm going to switch screens here. So we've got exactly the same f of x. There's our red 2 to the x graph, and exactly the same logarithmic graph. The blue graph is the log of x in base 2. But now I've made a couple sliders so that we can look at some specific points. Point P has an x coordinate from this slider. So let's look at that again. If I move it to somewhere where you can see it here, when a is 1, what is 2 to the first power? That would be 2. And here's our ordered pair, 1, 2. If I put the slider at 3, what is 2 to the third power? That would produce 8. So our values on the red graph were getting larger. Let's try again the negative exponents. What if we put in -2? So 2 to the -2 power should be 1/4, and there it is in decimal form, 0.25. Okay, our logarithm graph, I'm using this slider B, so their colors would match. And look at where it is right now. B is equal to 8. So think what we're doing here. We're putting 8 in for the x coordinate. So what exponent on 2 turns it into 8? So do you see why our y coordinate is at 3? So let's leave b at 8, and then let's move a back to 3, and let's compare these two. Look at where they are geometrically. This green segment connecting them is bisected by this line, and that line is the diagonal. Y equals 1x. It has a slope of 1. So this is our 45-degree line. So these 2 points in geometry, you call this a reflection. P and Q fold across that diagonal line. And notice that P has the coordinate 3, 8, and Q has the coordinate 8, 3. And that's what we're trying to investigate, that exponential graphs and logarithmic graphs are inverse functions. There's a memory test from Algebra 1. Do you remember that inverse functions swap the x and the y variables? Before we proceed, let me just make one more attempt here at looking at some of these fractional values, what's happening here as we go down the list here. So as we're going down this part in here, so think what would happen on function g if I wanted to come up with a value of -2. Let's see if I can stop the slider at -2. So what exponent would it take to come up with -2? You can see how we come up with a problem. Is there any value, any exponent on 2 that will turn it into a negative number? So there we've got a problem. So that explains why this blue graph never crosses and never goes to the negative side, because when we're looking for exponents on 2, our results can only be positive. So there's a huge part of the lesson that logarithms, we've got to stay on the positive side of the graph. So logarithms are on the positive side of the y-axis. Exponentials up here stayed on the positive side of the x-graph. So you will get used to seeing the shape of exponentials rising, logarithmic graphs rising, but they fold over the 45-degree line. Okay, let's go back and try a couple of these on our own. Let's compare, again, an exponential function and a logarithmic function, and they should have a lot in common. So we're doing the exponential function with 5 to the x power, and the logarithmic function with 5 as the base. So both of these have 5 as the base. So we simply have to reverse our thinking. So very quickly here, I think you're can very easily do this exponential. 5 to the -2 power, we square it and we flip it over. 5 to the -1 power. 5 to the 0 power. Anything to the 0 power produces 1. 5 to the first power. 5 to the second power. So let's get our graph here. I'll slide it up from where I was going to graph. -2, 1/25. We almost can't even draw it because it's so close to the axis. At -2, our height is only 1/25. At -1, it's a little higher. It's at 1/5. At 0, we're at 1. And that point is always going to show up because any number to the 0 power will produce 1. When x is 1, we get a y coordinate of 5, and then very quickly we're off the graph. So 2, we're way up at 25. So these exponential graphs rise very quickly. And we can then draw a dotted line here to show you that this axis, which is y equals 0, is called an asymptote. It gets very close to that axis, but it really is never going to touch it. Okay, now let's switch to logarithms. So we have to reverse our thinking and say what exponent on 5 produces a result. What exponent on 5 produces 1/25? That would be -2. What exponent on 5 produces 1/5? What exponent on 5 produces 1? That would be 0. What exponent on 5 produces 5? Well, that's easy. That's a 1. And what exponent on 5 produces 25? So let's see if we can get these graphed very quickly. And we'll do that in our next video.